Hi everyone. Over the past few weeks, we've been talking about area between curves and then how to turn that area into a volume. Today we're going to go back to the very beginning and chat once again about how to find just the area beneath a curve. So you might recall that what we did in the very first place was we said, oh, okay, let's have some curve here. And I want to approximate the area maybe from A to B. And it was pretty tough at first to figure that out, so what we did was we said, oh, let's just draw in some rectangles here, and these rectangles will pretty much approximate that area. And we quickly found that this approximation wasn't so hot. We got a lot of gaps here and other things like that, and it was especially bad when there were only a couple of rectangles. Now, we figured out some ways to make it better. We could have lots more rectangles, or we could have midpoint rectangular approximation instead of left that we have here, and so on and so forth. But let's just consider one quick example here. Let's say I have a function that just looks like this, and maybe you recognize it as some kind of square root function here, and that's fine. And I'm going from maybe 1 all the way up to 4, let's say. If I wanted to approximate this with a rectangle, just one rectangle, let's see how bad this approximation is, right? Oh, it's awful. Look at all this extra space. And if I wanted to approximate it even with the midpoint, it's not going to be so great. So the question is, can I use a shape that's not a rectangle to get a better approximation? And, spoiler, I already told you what shape it is. So what if, instead of making this a rectangle, we made it a trapezoid? Well, we recall that a trapezoid looks like this. Wow. Look how much better that approximation is. I mean, there's still a little gap here, but even with just one trapezoid, we see how way, way better this is than one rectangle. And so many trapezoids obviously will be better than one, but one trapezoid much better than one rectangle. So many trapezoids much better than many rectangles. And we'll just continue along this line of thought and do an approximation or two. Hopefully it shouldn't be too bad, having seen lots of these approximations before. So let's pick our favorite function to start with. What is our favorite function? Today, our favorite function is going to be f of x, and we'll say it's equal to 2 square root of x. Okay. Square root x, we know what that looks like. The 2 out front just does a vertical stretch, so it makes it a little bit taller than it would have otherwise. So it looks very similar to the picture that we just had here. Whoops, there it is. And let's say we want to approximate this on the interval, and let's just keep the same interval that we had before, from 1 to 4. And because this is our first time through, let's pick a really nice number of trapezoids. Let's pick 4 trapezoids. So I want to know, and I'm going to call this, and I know this is weird, but I'm going to call it TRAM. For whatever reason, we call it TRAM and not just TAM, right? RAM we talked about being rectangular approximation method. This is going to be trapezoidal approximation method, which is the same thing. And we're going to find TRAM 4, because there are going to be 4 trapezoids here. Okay, so let's do it. So that means I need 4 partitions. 1, 2, 3. Oh, maybe I should make it 3. Make it even nicer. Let's have it be TRAM 3. Sorry about that. And then we'll just sketch in our trapezoids here. Whoop, whop. The first thing that I need to recall is, what is the area of a trapezoid? Well, okay, so the area of a trapezoid is 1/2 times the height times base 1 plus base 2. And it's important that we remember things like the bases of a trapezoid are the 2 sides that are parallel to each other. So if I look at this particular trapezoid here, this very first trapezoid, the bottom is not the base. Right? The bases are here and here. These are the two bases. This bottom actually represents the height because it's perpendicular to both of the bases and connects them. We recall from RAM notation that this is going to be my delta x, and in this particular case, 2, 3, 4, it's equal to 1 for all of my trapezoids. B1 plus B2 is what I'm going to figure out here, and it's not going to be so bad, because all I need to do is say, oh, this length is B1, and that's just f of 1. And this length is B2, and that's just f of 2. So the first area is going to be 1/2 times 1 times f of 1 plus f of 2. The second area will be 1/2 times 1 times f of 2 plus f of 3. And the third area will be 1/2 times 1 times f of 3 plus f of 4. And this is going to be the general procedure for how we do any of these problems. And of course we can plug in values for f of 1, f of 2, f of 3, and f of 4. Shouldn't be so bad. So let's do it. F of 1 is 1. F of 2, it's 2 times 1, which is 2. F of 2 is 2 square root 2. This is also 2 square root 2. This is 2 square root 3. That's 2 square root 3. And this is 4. And then I can tidy it up a bit and simplify it. So let's see. 1/2 times 2 is 1. I get half of 2 root 2 and another half of 2 root 2. So I get 2 root 2. I get half of 2 root 3. And I get another half of 2 root 3. So I get 2 root 3. And then I get half of 4 plus 2. And I could clean it up slightly and make this 1 plus 2 be equal to a 3. But this would be my area, units squared. That would be my area. Nothing terribly exciting or terribly new here, just summing things up. You might notice that in each one of these cases, I had 2 copies of my f of 2 and my f of 3. And I only had 1 copy of f of 1 and f of 4. And this will always be the case. I'll always get just 1 of my starting values and 1 of my ending values. But in the middle, this base will be shared by 2 different trapezoids, so it'll show up twice. So in general, I can get this nice formula here that says, okay, I'm going to have 1/2 delta x, which is 1/2 times the height, which I have in every single term. I'm going to multiply that by f of a, which is my starting point, plus, and then I'll get 2 of the next term, and my next term we'll call f of a plus delta x, because, well, I started at a and I moved to the right delta x. And then my next term I'll get 2 of those as well. I'll have 2 f of a plus 2 delta x. And I'll keep getting these 2 f of a plus 3 delta x, 2 f of a plus 4 delta x, and so on and so forth. So I'll put plus ... until I get all the way up to f of b, which is the end point of my interval. And I only get 1 f of b because, right, I only use this base exactly once. But this is my nice formula. Maybe it doesn't look so nice, but it's pretty okay to just do out by hand, just like when we did the RAM stuff. Wasn't too terrible. So let's do one more example, and then we'll be all done. Let's say I have a function here, and my function's going to be regular old x squared, and it's going to be on the interval -2 to 2, and I want t ram oh, let's say 8. Okay, and I'm not going to actually do out this calculation. I'm just going to set it up, and we can take it from there. So let's sketch this. Here we go. We're going from -2 all the way up to +2. Okay, and we want 8 trapezoids. So I'm going to make 8 partitions. Let's see here. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4, 8. Awesome. You'll notice the really, really cool thing about trapezoids is that when my function changes from decreasing to increasing, my trapezoids change with it, right? We used to have an issue with RAM where we wouldn't change with it, and so it would give us this weird thing where all the rectangles would be under every time it was decreasing and be over every time it was increasing, or vice versa. If it were increasing in this particular way, with concavity up. But you'll notice that with trapezoids, once we switch from decreasing to increasing, the trapezoids themselves switch and really hug this curve very, very nicely. It's pretty cool, right? We saw that every nice function can be approximated with a tangent line. These are just almost tangent lines, not quite. They're secant lines because they connect 2 points on the curve. But they are really good approximations for the curve at this particular point. And you can see, even in this picture, you have a hard time distinguishing between the trapezoid and the curve itself, which means it's a pretty good approximation. So let's go ahead and figure this out here. So it should be 1/2. My delta x, well, there are 8 of them, and the interval is 4 units long, so that's going to be 1/2. I'll get this times f of -2 plus 2f of -1.5, plus 2f of -1, plus 2f of -0.5, plus 2f of 0, plus 2f of 0.5, plus 2f of 1, plus 2f of 1.5, plus f of 2. And none of these values should be particularly hard to compute, especially given that you have this function. For instance, f of 1.5 is 2.25. 1/2 times 1/2 is just 1/4, and I can plug all of these into my calculator and solve it straight away. So this is how we'd go about a trapezoid rule problem. Trapezoid approximations, again, really quite good. You might run into these on the AP exam or something similar. So for class today, we're just going to spend some time on this particular rule, and we're going to re-emphasize the fact that how did we find integrals? We found them from taking shapes like this. We actually took rectangles, and we kind of collapsed them on themselves to make them a bunch of just line segments, almost as close to line segments as you can get, and we added up the width of all those. In a similar way, right, what we've been doing recently has been finding areas and adding up all of those areas to get a volume. So this is kind of another way to think about integration, which is integration that kind of adds one dimension to the thing that you're dealing with, right? If we collapsed these on each other and made them line segments and added them all up, we'd get this nice area. If we kept a shaded region and revolved it around an axis, and we added up those areas, the cross-sectional areas, by an integral, we'd get a volume. So another great way to think about integration is adding a dimension to whatever units you have. All right, great. Well, that's it for now, and I'll see you in class.